This is a video about first-order interpretations in model theory. First-order interpretations are a very flexible tool to construct new structures from old ones. The definition of first-order interpretations is a bit technical, so I first start with some examples to guide your intuition. The first example of an interpretation will be a construction that you all know, namely the construction of the rational numbers in the integers. The idea is that every rational number can be represented by a pair PQ of integers. One number is for the numerator and the other for the denominator. Of course, the denominator should not be 0, and different pairs of integers might represent the same rational number. All this is still informally speaking. I haven't defined yet what a first-order interpretation is. Our second example of an interpretation will be a beautiful and useful concept in graph theory, namely the line graph of a given graph, G. The line graph of G is defined as follows. The vertices of the line graph are defined to be the edges of G. Two vertices of the line graph are joined by an edge if the respective edges in G have a common endpoint. Our definition of interpretation is supposed to be a common generalization of these two constructions, and many more. Let A and B be two structures, possibly with different domain and different signature. A first-order interpretation, or short, just an interpretation, of B in A is a partial surjective function, I, from A to the D to B, such that certain properties hold. Here, D is some natural number called the dimension of the interpretation. By partial, I mean that I need not be defined on all of A to the D, but just on some subset. However, every element of B must lie in the image of I. The idea is that a D-tuple, T, in the domain of I, simulates the element I applied to T. The conditions basically formalize what it means that also the relations and operations of B can be simulated by A. For every atomic formula phi, with three variables x1 up to xk, over the signature of B, there should exist a first-order formula phi subscript I with k times d many variables. The formula has k times d many variables because every element of B is simulated by a d-tuple of elements of A. The condition that we impose is that A satisfies phi sub I on some elements A11 up to A subscript D superscript K if and only if B satisfies phi on the image of these points under I. That is, I applied to A11 up to A sub D superscript 1 and so on until I applied to A subscript 1 superscript k A subscript D superscript k. Note that we require the existence of such a formula phi sub I for all atomic formulas phi over B. In particular for the atomic formula x equals y. This will be important, as we will see later. Let's have a look how this definition captures the examples that we have seen earlier. I claim that the field of rational numbers has a two-dimensional interpretation I in the ring of integers. The domain of I consists of all pairs of integers such that the second entry is non-zero. And I maps such a pair x1, x2 to the rational number x1 divided by x2. We have to check that this is indeed an interpretation. So for each atomic formula over the rationals, we have to find a defining formula over the integers. For the atomic formula x equals y, the defining formula must have 2 times 2, so 4 variables. First, we have to say that the denominators are distinct from 0. We would now like to express that the rational number x1 over x2 equals the rational number y1 over y2. However, we do not have division in our signature. But it's not a problem, since we can express the same fact using multiplication, namely as x1 times y2 equals x2 times y1. We simply multiplied both sides. with the product of the denominators. Likewise, we can find an interpreting formula for addition. We can express the atomic formula x plus y equals z by a formula with 6 free variables over the integers, by, again, first excluding 0 as a denominator, and then multiplying both sides of the equation that we would like to express by the product of the denominators, and obtain an expression over the integers using only multiplication and addition. Finding formulas for multiplication and the formula x equals 0 and the formula x equals 1 is similarly straightforward. So indeed, Q has an interpretation in Z. The line graph of a graph G has a two-dimensional interpretation in G. We view G as a relational structure with a binary relation symbol E for the edge relation. Then the domain of our interpretation is the set of all edges of G. And we map a pair x1, x2 to the two-element subset x1, x2. Also in this example, we start with the atomic formula x equals y. We have to find a formula with 4 free variables x1, x2, y1, y2, which holds on two pairs if and only if they represent the same vertex of the line graph. For this, x1, x2 and y1, y2 should form edges. They represent the same undirected edge if either the start points and the end points of the two edges agree, or if the start point agrees with the end point of the other edge and the end point agrees with the start point of the other edge. For the atomic formula EXY, the interpreting formula again starts with formulas that assert that x1, x2 form an edge and y1, y2 form an edge. These two edges are adjacent in the line graph if they share a vertex, but are distinct. There are 4 possibilities for this, and these possibilities can be spelled out by first-order formulas. For example, if x1 equals y1 and x2 is different from y2, then there is an edge. Similarly, there is an edge if x1 equals y2 and x2 is different from y1. And there are 2 more cases where the overlap happens at x2, which did not fit on the screen. So we conclude that the line graph of any graph G has an interpretation in G. I present another example, known as Allen's interval algebra in artificial intelligence. Allen invented this formalism to model how agents qualitatively reason about events in time. This formalism can be viewed as a structure whose domain consists of all closed, bounded intervals over the rationals. The structure carries several binary relations. For example, a binary relation P, which stands for precedes. So P of xy holds if x denotes an interval that comes strictly before an interval y in time. We also have a binary relation D, which stands for during. D of xy holds if x denotes an interval that starts later and finishes earlier than an interval y. We also have relations for overlap, for meets, for stars, and a couple of more relations that don't fit on the screen. I claim that this structure has a first-order interpretation in Q. Again, I will present a two-dimensional interpretation. The idea is that I represent a closed, bounded interval by its start point and its end point in Q. So the domain of my interpretation is the set of all pairs xy, where x is strictly smaller than y. The interpreting formula for precedes, for P, has 4 free variables, x1, x2, y1, y2. But actually we only need to impose constraints on 2 of the variables, namely we have to impose that x2 is strictly smaller than y1. So the end point of x is strictly before the start point of y. And similarly, we can write down interpreting formulas for during, overlap, meets, starts, etc. I already mentioned that if B has an interpretation in A, then B often inherits properties of A. An example of this type is the property of omega-categoricity. Suppose that B has a d-dimensional first-order interpretation in A. Then it holds that if A is omega-categorical, then B is omega-categorical. This is straightforward from the characterization of omega-categoricity of countable structures in terms of their automorphism groups, from the theorem of Relnatsevsky. We have to show that the automorphism group of B has finitely many orbits of n tuples, for all n. But we already know that the automorphism group of A has finitely many orbits of d times n tuples. And this provides an upper bound on the number of orbits of n tuples in the automorphism group of B. As a corollary, we obtain that, for example, Allen's interval algebra is omega-categorical. We already know that the order of the rational numbers is omega-categorical. And since Allen's interval algebra has an interpretation in the ordered rationals, the omega-categoricity of Allen's interval algebra follows immediately from the proposition above. Interpretations can be composed. If C has an interpretation in B and B has an interpretation in A, then C also has an interpretation in A. If J is an e-dimensional interpretation of C in B and I is a d-dimensional interpretation of B in A, then we obtain a d times e-dimensional interpretation of C in A by composing the maps of the interpretations in the obvious way. We first apply I to d tuples of arguments, and then apply J to the resulting e tuple. To check that the resulting map is indeed an interpretation, we construct an interpreting formula for an atomic formula phi over the signature of C as follows. We first consider phi sub j, the interpreting formula of the interpretation J, and is a formula over B. Then we translate phi sub j into a formula, which I call phi sub j composed I, over the signature of A as follows. Each variable x will be replaced by d new variables x1 up to xd. Each atomic subformula psi will be replaced by psi sub I. If phi has k free variables, then phi sub j composed I has k times d times e free variables. And it is easy to check that this is a defining formula for phi in A with respect to j composed I. Two structures A and B are called mutually interpretable if B has an interpretation in A and A has an interpretation in B. Note that mutual interpretability is an equivalence relation by what we have just seen. It is a relatively coarse equivalence relation. For example, any two finite structures with at least two elements are mutually interpretable. Or any countable structure with the empty signature is mutually interpretable with an equivalence relation with infinitely many infinite classes. These are easy exercises. We want to define another equivalence relation called bi-interpretability, which is much finer. Two structures A and B are called bi-interpretable if first of all they are mutually interpretable. That is, there is an interpretation I of B in A and an interpretation J of A in B. Such that additionally, I composed with J is definable in B, and J composed with I is definable in A. Formally, suppose that I has dimension D and J has dimension E. We require, formally, that the relation of arity D times E plus 1, that contains all tuples where the first entry is the function value of the remaining entries under I composed with J, is definable in B. Similarly, we have such a relation which should be definable in A. One of the motivations for this definition is that if A and B are bi-interpretable, then the automorphism group of A is isomorphic to the automorphism group of B as abstract groups. So there's a bijection between the automorphisms of A and the automorphisms of B that preserves composition in the group. As a simple example of two structures that are bi-interpretable, let's consider the countable structure with the empty signature and the structure whose domain is the set of all pairs of natural numbers and which carries a single binary relation, namely the relation that contains all pairs of pairs such that the second entry of the first pair equals the first entry of the second pair. Let's call this relation M. It is relatively easy to see that the two structures are mutually interpretable. One interpretation of the second structure in the first is the identity map. One interpretation of the first structure in the second structure is the projection map that maps a pair to its first component. If we first apply I to a pair x, y, and then j, we get back x. And the relation x equals z is clearly definable. So this part of the bi-interpretation is clear. The situation if we first apply j and then I is much more interesting. So we have a pair u and a pair v. And we would like to define that I composed with j applied to these two pairs equals some other pair w. So we have to express that the first entry of u equals the first entry of w, and that the first entry of v equals the second entry of w. That the first entry of v equals the second entry of w is easy to express with the relation m, by m applied to wv. To express that the first entry of w equals the first entry of u is more interesting. We cannot express this directly, but we can existentially quantify a pair p and then express that the first entry of w equals the second entry of p, and then that the second entry of p equals the first entry of u. By transitivity of equality, we have then expressed that the first entry of u equals the first entry of w. So altogether, we find a first-order formula that defines I composed with j in the second structure. And this concludes the proof that we have a bi-interpretation here. Our next example shows two structures that are mutually interpretable but not bi-interpretable. Again, one of the structures is countable with the empty signature. The other structure carries one binary relation. This time the relation contains all pairs of pairs where the first entries are the same. Let's call this relation n. Again, it is easy to see that the identity is an interpretation of the second structure in the first, and that the projection to the first entry is an interpretation of the first structure in the second. To see that the two structures are not bi-interpretable, we consider the automorphism groups of the two structures. Note that the relation n is an equivalence relation with infinitely many infinite classes. The second structure has an automorphism group G with a non-trivial normal subgroup H, namely the subgroup of all permutations that fix each equivalence class of n setwise. By non-trivial, I mean that it has more than one element. It is easy to see that the quotient of G by H is the full symmetric group on a countably infinite set. The automorphism group of the first structure is the full symmetric group on n. The non-trivial normal subgroups H of this group have been classified by Schreier and Ulam. There are precisely two. But from the description of these normal subgroups, it is clear that the quotient of G by H is not isomorphic to the full symmetric group. Therefore, the two structures are not bi-interpretable.